I'm Anil Kumar. Welcome to my international series on Combinatorics. We are going to discuss about factorials in this particular video. You can always contact me on my email or on the website globalmathinstitute.com. We'll at length discuss about factorials, starting from the basic definition to some simple problems and then examination type questions. We'll also derive many relations which will help you solve many difficult questions which could be expected in any international exam. So we'll begin with what basically n factorial means. What is this factorial notation? So you must have seen something like 7 factorial, right? It really means you just multiply the natural numbers 7, 6, 5, 4, 3, 2, and 1. So you get the product of this, which is in short written in factorial notation as 7 factorial. So that is what it is. So this exclamation mark is the notation for factorial. So you can see here a continued product of first n natural numbers is called n factorial. So that is what is factorial notation, right? So n factorial. So it is denoted by n factorial, and I've written here 7 factorial is 1 times, 2 times, 3 times, 4 times, 5 times, 6 times 7. You get a number. So factorial will give you a natural number as the output. Now, in general, n factorial could be written as product of numbers 1 to n, either this way or the other way. Both work the same, as the product is, you can say, associative, right? So there are many which are getting multiplied. Okay, here's a very common question, which is, what is 0 factorial? Is it equal to 1? Yes, it is. How do you prove it? We are going to see that. And n factorial can be also written as n times n minus 1 factorial. And likewise, we have many other relations which relate n factorial, n plus 1 factorial, n plus 2 factorial. Their difference with n factorial, correct? So, and some expressions where we will have them as quotients. So we'll see how to solve all these questions and many more in this particular video. Now we'll also see how do we write NCR, right? That is the basic for n choose R. Now you know the rule, which is the sum of the previous two, right? You have seen this in Pascal's triangle, binomial coefficients, all these things are related. We have a factorial term in these, right? We will work with that also. Some of you might take that up after this lesson. Some might have been introduced to it already. We'll also take some examples which are kind of like this. So now let's begin for this session on factorials. The very first thing is, how do we calculate each factorial, right? So here is a very easy method to calculate all the factorials. We'll begin with 0. Okay, so as I was saying, 0 factorial is 1, right? So we have written numbers here which are non-negative integers, since we used 0 to begin with. Okay, so 0 factorial, as you know, is 1, and now the next number will be 1 factorial, means 1 times 0 factorial, right? So 1 times 0 factorial is going to give us 1 only, and then next number will be 2 factorial, which is 2 times 1 factorial. So you are multiplying with this factorial product with the number to get 2 factorial. 3 factorial will be 2 factorial times 3. 4 factorial is 3 factorial times 4. 5 factorial is 4 factorial times 5. So the number gets multiplied by the factorial value which you just got. So if you have to get 7 factorial, you know 6 factorial is 720. Multiply 720 by 7 to get 7 factorial, which is 50 40. Likewise, you can continue and fill up your table. Anyway, that is how easy it is to calculate such a big number which we are talking about, correct? Here, it was interesting to see that we always took n factorial value as the number multiplied by n minus 1 factorial. So we have already utilized one of the important characteristics of this particular series. Now, let's take another example where we are going to take basic operations with factorial, right? So here are a few things to be calculated. The very first one is, what is 4 factorial square? Clearly, I should first find the value of 4 factorial, which is 4 times 3 times 2 times 1, and then I get 24. Square that. Square of 24 is 576. That becomes your answer. How about 10 factorial divided by 8 factorial? Well, 10 factorial can be written as 10 times 9 times 8 factorial. Do you see that? So we have 8 factorial in the denominator. They cancel and you're left with 10 times 9, which is your answer, 90. Here we have 3 factorial and then factorial, right? So definitely I should first work out the inside 3 factorial, which is 3 times 2 times 1, 6, and then we'll see what 6 factorial is. Clearly the answer is 720, as you can see here. Perfect. That is how we can do some elementary operations with the factorial. I hope you got conversant with it. Let's move forward and get ready for much more of this coming now. Now this example 3 is to convert products to factorials. We have 8 times 7 times 6 times 5 times 4. How can I write it in the factorial form? Well, 3 to 1 is missing, so I multiply by 3 to 1 in both numerator and denominator. Once I do that, on the top I have 8 factorial and in the denominator I have 3 factorial. Wow! So I've written this number as 8 factorial over 3 factorial. Now another series is 2 times 4 times 6 times 8 times 10. All are even numbers. How do I write this as a factorial? Well, all of them are even numbers. 2 is 2 times 1, 4 is 2 times 2, 6 is 2 times 3, 8 is 2 times 4, and 10 is 2 times 5. How many 2's do I have? 1, 2, 3, 4, 5. So I'm writing this as 2 to the power of 5, and rest of the numbers which are being multiplied are 1, 2, 3, 4, and 5, which is 5 factorial. Correct. So I get my answer 2 to the power of 5 times 5 factorial. So the even numbers, when you multiply, do you see a pattern right there? This is a very important pattern. We are going to explore this further in the coming examples, and I hope you got the idea. Can you write a general formula for this? You should be in a position to do it. Perfect. Now let's move on and take up the next example. Here is a very exam test question which is very popular. 1 over 8 factorial plus 1 over 9 factorial plus 1 over 10 factorial is equal to x over 11 factorial. You need to solve for the value of x. How would you do this? You can pause the video, try to answer this question, and then move forward. Okay, well, what comes to my mind is to multiply by 11 factorial all the values, right? All the terms. So I did that. So we have 1 over 8 factorial plus 1 over 9 factorial plus 1 over 10 factorial equals to x over 11 factorial. So I multiplied each term by 11. That isolated x, correct? Right. So now it's easy. I know x is on the one side. I have to now simplify the left hand side. 11 factorial over 8 factorial. Does it remind you of something? Yes. I can write this as 11 times 10 times 9 times 8 factorial. And this 8 factorial will cancel, right? That is the strategy. So most of the questions involved with the factorial, you could rewrite this in a simplified way and then cancel some terms. 11 factorial this time will go up to 9 only. So 11 times 10 and then keep 9 factorial so that it can be cancelled. And then we have again 11 factorial. Denominator is 10 factorial. So we'll write this as 11 times 10 factorial. Result will be 10 factorial cancel. In the previous one 9 factorial and then in the first one 8 factorial. So the factorial terms have really got cancelled now. You're left with few numbers to work with. 11 times 10 times 9 gives you 990. 11 times 10 is 110 and then you have number 11. When you add them up, what do you get? You get a very beautiful number 1111 and that is the value of x. Correct? So in this particular example, what do we get? We get x is equal to 1111. Correct. Now let's talk about 0 factorial. Correct? As you know, 0 factorial should be 1. It cannot be 0. You cannot divide by 0, right? If you multiply by 0, everything becomes 0. Correct. We don't have 0 here. We are working with very, very big numbers. So how do we prove that 0 factorial actually is 1? Okay, let's look into this proof. So as you know, n factorial can be written as n times n minus 1 times n minus 2 times so on times 3, 2, 1. And we also saw that this could be written as n times n minus 1 factorial. That is the key, correct? So we can write 3 factorial, for example, as 3 times 2 times 1, which is 6, or 3 times 2 factorial using this particular rule. Okay, so 3 times 2 factorial, which is 6. How about 2 factorial? Well, 2 factorial is 2 times 1 factorial. The value is 2. Similarly, 1 factorial should be 1 times 0 factorial. And the answer is 1. Well, remember, only 1 times 1 is equal to 1. You're saying 1 times 0 factorial is 1. That means what? Clearly, that means that the value of 0 factorial should be 1, right? So that is how we conclude that 0 factorial is in fact just 1. Very important result. Okay, so note, 0 factorial can be proved from the concept of NCR, n choose 0, right? So when you learn about combinatorics, and especially the combinations of picking up nobody or nothing from a group of n elements, there's only one way to do it, not to choose any one of them. And that also gives you the answer that NC0 should be equal to 1. That's another way of doing it. And third way is the formula itself. So if we have NC0, it is given as n factorial divided by n minus 0 factorial times 0 factorial. Well, 0 factorial has to be 1 to make the statement true. And that is why it is 1. So there are so many ways. 3 you have seen here itself. Let's move on to a very, very interesting question. Example 6. Write a single factorial. But this time we have taken a very beautiful example, I should say. The question here is a formula to find the number of seconds in 6 weeks can be derived as being shown here. Basically, we want to figure out that in 6 weeks, how many seconds are there? That is what we're trying to figure out in this particular formula. And we get the answer as 10 factorials. See how are we working to get this answer. This is key to write product of many numbers in factorial form. You can come up with many interesting cases. Here is one of those beautiful ones. Now, we want 6 weeks. 6 weeks can be converted to days. We know there are 7 days in a week, correct? So multiply by 7 and then a day has 24 hours, multiply by 24. Now every hour has 60 minutes, multiply by 60. And every minute has 60 seconds. So multiply by 60 again. Therefore, we can write that 6 weeks period as 6 times 7 times 24 times 60 times 60 seconds. So that is what we have. Now, the idea is to write this in factorial form. How can we do it? That's the beauty. Have a look. So we begin with this set of products, which is 6 times 7 times 24 times 60 times 60. Now we already have 6 and 7, no problem. So we have the 6 and 7, that is fine. Then the number 24, what did I do with that? Okay, this number 24 we wrote as 8 times 3. Right, we want to break them up into smaller numbers. Sometimes it is even better to actually combine some numbers. So 60 times 60 has been written as 3600. Well, now you can observe that we have 6 times 7 times 8 times 3. Some numbers are missing. So we have to expand 3600 to get other numbers. So let me just copy these numbers which we already have, which are 6 times 7 times 8 times 3. Now, as far as 3600 is concerned, 36 is 9 times 4. So we got two more numbers and 100. Okay, so now we have 9 times 4, 6, 7, 8, and 3. About 100, we have to get rest of the numbers to make it 10 factorial. 100 is 10 times 10. Okay, 10 is 5 times 2. So that makes sense. So what we are going to do is we'll write 100 as 10 times 5 times 2. Once we do that, do you see you have all the numbers from 1 to 10 in your list? I do see that. That's beautiful. So that is your list. Once you rearrange, you get this set of 1 times, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, 10, which is in fact 10 factorial. And so we get our answer. 6 weeks has 10 factorial seconds. Do you see that? That's the beauty, right? So you can figure out many more terms and write them in factorial notation. Okay, now let's look into the next one. Here is again a very beautiful example. Here is a very interesting pattern to talk about where we'll show that the following results are correct. And what are the results? 10 factorial is written as 9 factorial plus 8 factorial times 9. Okay, and what is 9 factorial written as? 8 factorial plus 7 factorial times 8. And 8 factorial as 7 factorial plus 6 factorial times 7. 7 factorial as 6 factorial plus 5 factorials times 6. Wow, what a series. So basically, I can write n factorial as n minus 1 factorial plus n minus 2 factorial times the number n minus 1. Wow, can it be true? Okay, let us check. Let's check this very first one. 10 factorial, they say, is 9 factorial plus 8 factorial times 9. Let's check it out. So first thing is our strategy. We have to expand the factorial slowly and slowly. So 9 factorial can be expanded. So in this particular case, let's begin with the right hand side, which is 9 factorial plus 8 factorial times 9. So what I'm doing here is that I'm going to write 9 factorial as 9 times 8 factorial. And now we have 8 factorial as common. So we took 8 factorial common. We get 9 plus 1. And outside we have the number 9 itself. Good. So we landed with 8 factorial. And 9 plus 1 is 10 times 9. And when you multiply them, 10 times 9 times 8 factorial is in fact 10 factorial, which is the right hand side. So that is how you actually write this particular expression. So it is true, correct? It is absolutely true. So we just saw that 10 factorial can be very easily written as combination of 9 factorial and 8 factorial multiplied by 9. Correct. Now, it's good time to straight go to the proof of the general expression, which is n factorial will be equal to what? It should be n minus 1 factorial plus n minus 2 factorial and everything multiplied by n minus 1, the number. That is what we are going to prove it. How are we going to prove it? Well, we'll split n factorial in a way so that we get all the terms. Perfect. So we want to prove that n factorial is all this. We'll begin with left hand side just as we did with 10 factorial. We have a strategy here, correct? So the strategy clearly is that the number n minus 1 factorial has to be broken down as product of 2. N minus 1 times n minus 2 factorial. Since we have done this, we know n minus 2, n minus 2 factorial is common. We can take that common outside. Within the bracket, we are left with some numbers, and those numbers can be simplified to get the result, which is right there, which looks like n factorial, the right hand side. So I hope that makes sense. You can at this stage pause the video, go through this proof once again. That gives you an insight to the type of proofs we are going to see in this particular chapter. Perfect. So let's move on. Oh my God. So there are so many examples in this particular page to do. I'd like you to pause the video at this stage and then answer some of these yourself. One more thing is these are very important questions. Make a note of these and use them as rules. So here example 11, simplify factorials. Show that the following results are correct. Well, our results, I didn't write the answers here, but we solved, for example, the first one, which is n factorial squared divided by n plus 1 times n minus 1 factorial is equal to n over n plus 1. So that is the result which should go in your notebook in a particular order as I have written here. That is going to help you a lot in coming chapters also. Perfect. Now, let's talk about its proof first and then we'll move on. So the strategy is that n factorial square means n factorial times n factorial. That's the key. And now one of these n's, which is right there, is being expanded as product of n and n minus 1 factorial, correct? So we did that. Once you do that, there are many things which can cancel and so cancel them. So most of these factorial terms you can see are cancelling out. What are you left with? You're left with the terms which are not factorial and which look like n over n plus 1. Do you see that? How simple it becomes? That is how you have to do it. That's the beauty of this particular exercise. Correct. Now let's take up the next example, which is n factorial by n minus 2 factorial. Come on, what should be your strategy? Well, clearly, the numerator can be written as n times n minus 1 times n minus 2 factorial. That's the whole idea. Divided by n minus 2 factorial. Correct. And then cancel the factorial terms. You're left with the answer, which can be written in expanded form. Correct. N times n minus 1. That's what I got. N times n minus 1. You could write it like this or expand and write like a polynomial n square minus n. So many times in questions related to factorials, you will find polynomials as your end result. This is how you get them. So we did part B. Similarly, I will advise you to take up part C and D also. Strategies similar to B and A will be followed. For C, for example, n plus 3 factorial and n plus 1 factorial, that means what? N plus 3 times n plus 2 is your answer, right? The others cancel away. When you expand, you get a polynomial, quadratic, n square plus 5n plus 6. That is how you're going to do it. The next one is slightly different. This time we have n square minus 4. Well, think about n square as capital N. Still it is n minus 4, right? So you can write this as n square minus 4 times n square minus 5. Since minus 5 is there in the denominator, that will cancel away and you're left with n square minus 4 over n minus 2. And you know what this is. This is n plus 2 times n minus 1, which will cancel and you're left with n plus 2 as your result. Perfect. That is how you are going to do it. So I hope this is absolutely simple. However, these results can be utilized in proving more complicated questions. Perfect. Let's move on and take some important results. We'll prove them here, but you can always use them in your exercise. So here we will prove n plus 4 factorial minus n factorial is equal to n factorial times a polynomial of degree 4. Oh my God, how do we prove it? So what I did was I left that for you. Okay, so becomes a question for you. So I have not done this. It's a question, an exercise for you to do. However, I have shown you a method of doing it. So I began with n plus 1 factorial minus n factorial, where n plus 1 factorial, as you know, can be split and written as a product of n plus 1 times n factorial minus n factorial. You can take common n factorial and you get n plus 1 minus 1 in the brackets. 1 plus 1 minus 1 cancel. You get n factorial n as your answer. Okay, so that means n plus 1 factorial minus n factorial is n factorial minus n. This could be your first rule, for example. Okay, now let's take n plus 2 factorial minus n. So we are moving to n plus 4 slowly. So n plus 1, n plus 2, n plus 3, and now the next one will be n plus 4 to follow. However, the strategy is simple. N plus 2 factorial minus n will mean n plus 2 times n plus 1 times n factorial. Again, take n factorial. You have a polynomial which is common. Simplify and expand to get that polynomial with n factorial outside. So you're getting n factorial outside with the polynomial inside as we move along. And that is what is expected. Do you see that? In case of a cubic thing, n plus 3, you have three things to multiply now, right? N plus 3 plus n plus 2 times n plus 1. Clearly, when you multiply these three factors with n plus 3, n plus 2, n plus 1, you get a cubic equation or a polynomial with n factorial. And then if you continue this process, you'll get the solution which is asked for. So you can now multiply n cubed plus 6n squared plus 11n plus 5 with n plus 4. So that should be your answer, right? So you have here n cubed plus 6n squared plus 11n plus 5, and you could multiply that by n plus 4 to get your answer, which is given right there. Is that clear to you? That is how you could prove it. Perfect. Now let's move on and take very interesting question. So on this examination, there are different varieties. We have already covered 5 or 6 of them. And here is one of the most important, and that is find the compact expression for the sum. So now we'll find a compact expression for the sum series, right? We are moving from product to sum. Do you see this plus in between for all these terms with factorials? That is the sum series. So the very first one is 1 factorial times 1 plus 2 factorial times 2 plus 3 factorial times 3 plus 4 factorial times 4 plus 5 factorial times 5 plus n factorial times n. N factorial times n. Does that remind you of something? Let's go back. So what we have here is n factorial times n is equal to all this. Do you see that? We have just proved this result. We can use it to solve our question. And that's what I did. So that's smart. So this is a result which we have taken in example 12, which says that n plus 1 factorial minus n factorial is n factorial times n. And here we have a term, general term, which is n factorial times n. That should help us break down each factorial times that number using this difference. Do you see that? So here we have n plus 1 factorial minus n factorial equals to n factorial times n. Do you see that? So with this difference, we can actually converge the series and get our answer. We also call this as a telescopic approach to solve our questions. So let me write down the word. We are going to follow a telescopic approach. Is that clear to you, right? Using this particular formula right there. So what I did was, instead of writing 1 factorial times 1, we wrote this as 2 factorial minus 1 factorial. That's what it means. n plus 1 factorial minus n factorial means this, right? More than 1 is 2 minus 1 factorial itself. 2 factorial minus 1 factorial. Now, 2 factorial times 2 factorial will be written as 3 factorial minus 2 factorial. We'll continue with this series getting alternate negative terms. Do you see that? So what we have here is alternate negative terms. They will cancel out. Perfect. So when these terms cancel out, then you have a simplified version and you approach your answer. Do you see the result? Perfect. That is how we do it. So when we get this, now you can cancel the terms which could. So for example, 2 factorial cancels with 2 factorial. What do you notice? The last term gets cancelled. So the last term n factorial will get cancelled. Do you see that? 3 factorial cancels this factorial. What remains clearly is this 1 factorial right there and n plus 1 factorial. All other terms in between will get cancelled. So we get our result, which clearly is n plus 1 factorial minus 1. And that is what the result is. So this is equal to, as shown here, n plus 1 factorial minus 1. That is the answer for this particular series. Is that clear to you? Now, to verify this particular answer, we have part B of this question, which says, what is the result of 1 factorial times 1 plus 2 factorial times 2 plus 3 factorial times 3 plus 4 factorial times 4? Well, clearly, you can put this 4 factorial in the formula, right? 4 is your number. 4 plus 1 is 5. That means 5 factorial minus 1 is your answer. 5 factorial is 220 and 220 minus 1 is 119. That will be your answer. So you could do it like this, or you could prove it just as we did the others. So I have shown you the result right there for this particular question in two different ways, and there you go. One is the direct application of the formula and the other one is the result of what we derived. So I hope that is absolutely clear. So let's move on and take up the next question. This is one of the most interesting questions in the series, which says, do you need to prove 2n factorial divided by n factorial is 2 to the power of n times product of odd numbers. So this is odd number series. Do you see that? Very important note. And we have a power of 2 and then 2n factorial over n factorial. So let us see how to prove this. So we begin with the left side, which is 2n factorial over n factorial. When we have 2n factorial, then 1, 2, 3, 4 will go up to 2n, right? So up to 2n. Now what should we do? Clearly, we are looking at odd number and even number separately. Why don't we separate it out? So amongst these numbers, I am going to take away the even numbers and put them in a separate way, right? So these even numbers, these are even numbers. We make them as a different series, product of course, correct. And then we have a set of odd numbers which are there, 1, 3, 5, 7 till 2n minus 1. So we have that, and of course the denominator n factorial remains with us as such, correct. No change to the denominator. Now, it is interesting, as we did in one of our earlier examples, we have this series like, let me rewrite this, right? So we have the series like 2 times, 4 times, 6 times, 8 times, so on. This can be written as 2 times 1, 4 can be written as 2 times 2, 6 can be written as 2 times 3, 8 can be written as 2 times 4, and so on. So you see how many 2's you have? To the power of n. So what we did was, we took these 2's common. To multiply them. So we get the term 2 to the power of n. Right there. And what remains is these numbers 1, 2, 3, 4, 5, 6 till n. So we are left with those numbers, and this is n factorial. So we wrote them as n factorials. Rest is as shown above. and n factorial cancel, and we get our result. That is how we are going to prove this particular identity. Now, this is a very important identity which can be used in solving many questions if you can remember it. Otherwise, this is how you're going to prove it. So, once again, another very important formula we have come across. Now, let's begin with our combinatorics. So, in combinatorics, we have NCR, n choose R, which basically is defined as n factorial over n minus r factorial times r factorial. Now, here is a rule, which you also saw in Pascal's triangle. Every term is sum of the previous two. Similarly, the binomial coefficients are also related, since you know in Pascal's triangle you can have the value of each element by using binomial coefficients. Perfect. Or the other way, Pascal's triangle numbers can be placed to expand binomial coefficients, right? So we have to prove it. Now let us see how to prove it. NCR equals to n minus 1 CR minus 1 plus n minus 1 CR. These are the previous two, right? They add up to the next one. So let's expand n minus 1 CR minus 1 plus n minus 1 CR using the formula given above. So we are using this particular formula to expand. Now we need to simplify. The strategy here is to get something common. We see n minus 1 minus r on one side, and on the other side, when you simplify, we have only the term n minus r. So I could expand this and write this as n minus r times n minus r minus 1, and that becomes common with n minus r minus 1. So that becomes common. That is one part of it. The other part is we can observe that we have r minus 1 factorial and r factorial. That means I can change r factorial to r times r minus 1 factorial, making r minus 1 factorial common. So that becomes our strategy. We apply this strategy, take the common terms, and within the bracket. So these are the common terms which we have taken out within the bracket. We have terms which are independent of factorial notation, and they simplify to our result. That is how we are going to do it, right? And so we get our result, which is n minus 1 factorial over n minus r minus 1 factorial times r minus 1 factorial within brackets. We get n over n minus r over r factorial. Now here, many terms can still cancel, and you can simplify it further. So we have n times n minus 1 factorial in the numerator. The denominator, when you put these terms outside the bracket, will be n minus r times n minus r minus 1 factorial, and then we have r, and then we have r minus 1 factorial. Clearly, r times r minus 1 factorial is r factorial, and the first term combined two, we have n minus r factorial. N factorial over n minus r factorial times r factorial is NCR by definition, correct? That is where we began. So, and that's where we reach. So combination of the previous two is the result of the next one. So that is what we have proved here. Very important proof from examination point of view. The last question here is again seen in many exams. We need to now prove that 1 over 2 factorial plus 2 over 3 factorial plus 3 over 4 factorial plus 4 over 5 factorial and so on up to n over n plus 4 factorial is what? So the question here is to find the compact expression for this sum. This is what we need to figure out. Now, you're supposed to do this. So take a break, pause the video, answer this question, and then look into my suggestions. Correct. Now here is a different strategy altogether. You can actually use one of the results which we have already got, which is n factorial times n is what? You could use this, right? Let me just get back to the result which I'm talking about, which is this one, right? You could use this result directly and solve the question. N times n factorial is n plus 1 factorial minus n to solve this particular question, right? You could use this. But here we have taken another approach, and the approach is very beautiful. We are writing n as n plus 1 minus 1 and then bringing it into two rational expressions. Do you see that? So that is a strategy. To break a rational expression into a over one factor plus b over the other factor. And that's how we have done it very clearly just by splitting n, rather adding plus 1 and minus 1, and then making two rational expressions. So the idea over here is when you get this negative, then that gives you alternating negative numbers and positive numbers, right? So alternate sign. So as soon as you get alternate sign, you can converge to a result, right? Which is the telescopic approach. So you can adopt this telescopic approach to get your result. That's the whole idea. Perfect. And that is what we are going to do here. So now we have got two expressions and you know how to solve them or simplify them, correct? So we have split an, which is a general term, right, as n plus 1 over n plus 1 n factorial. Now n plus 1 over n plus 1, so that means you can write this as 1 over n factorial minus 1 over n plus 1 factorial, correct, as expected. So we got difference of the two, 1 over n factorial for an and the next number minus 1 over n plus 1 factorial. So we can now replace each term with this particular sequence and where an is n over n plus 1. So if I suppose put n as 1, I get 1 over 1 plus 1, which is 2 factorial, right? So, and which I can write, which is the first term. So a1 will be 1 over 1 factorial minus 1 over 2 factorial. And similarly, a2 will be 1 over 2 factorial minus 1 over 3 factorial and so on. So we get this series. So we have the terms a1, a2, a3, and a4, an you can say in general, and then replacing these terms with our a's. We know we have alternating opposite signs, they cancel, so we get 1 minus 1 over n plus 1 factorial as our answer. So that is how we are going to prove it. So that is another excellent method of a proof, right? You could always use the results which we have done. You have seen similar thing, correct? You could use this result also. Anyway, so we have come to an end of this particular video and you have seen clearly that as promised in the beginning, we have dealt with all the type of questions which you see on this particular page. It is a very extensive approach to understand factorials at length and solve many questions. So if you spend some time going through this particular video, I'm sure you will get most of the concepts. Feel free to write your comment, share your views, and if you really want to contact me and learn from me, you can always write to me on the particular email or register yourself on globalmathinstitute.com. Feel free to write your comments and share your views. Thanks for your time and all the best.